Welcome to the presentation of our paper entitled Tightening Network Calculus Delay Bounds by Predicting Flow Prolongations in the FIFO Analysis. I am Steffen Bondorf. I am with the Faculty of Mathematics at Ruhr University Bochum, and this is joint work with Alexander Scheffler, who is affiliated with Bochum 2, and Fabien Geyer, who is with the Chair of Network Architecture and Services of TU Munich, as well as Airbus Central Research and Technology in Munich, Germany. Network calculus is concerned with bounding end-to-end delays of packets that are sent over a network. To visualize that, we brought this figure here where we see that there is this property, the actual worst case end-to-end delay experienced in the network and the bound we compute on that delay. Important for network calculus, as it is deriving bounds, is the property of tightness. That is quantifying the gap between the worst case that might sometimes not even be known because computing it comes with too much computational effort, and the bound computed by network calculus. We have set out to reduce this gap, meaning we have set out to increase tightness of the analysis. We are not the first to do so. There are quite some analysis methods in the literature, and the proposed methods reveal a general trend, that is, the tighter the result, the more computational effort the analysis demands. That means we are usually not in this ideal area with an analysis providing great tightness for little computational cost. In this paper we have set out to find a new analysis method that gives us a better trade-off between these two aspects. Network calculus is also known as a deterministic queuing theory, and it operates on a basic queuing model shown here on the right of the slide. There are data arrivals that enter a queue. The queue is served by a server, creating departures from this queuing system. And network calculus uses cumulative functions to count the arrivals and the departures to set system. On the left there's a visualization with an arrival function and a departure function, both being cumulative, making it easy to bound the delay with the horizontal deviation between the two curves and the backlog with the vertical deviation. Network calculus is concerned with bounding delay and backlog in such a queuing system, and therefore it already starts with bounding functions that describe the arrivals and the departures. There is, on the one hand, the arrival curve that in interval time, this time interval in the definition defined as t minus s, bounds the maximum of data arrivals. And similarly, there is a so-called service curve that is responsible for lower bounding the outputs, the departures of the system, also in interval time and based on the input to the system. Definitions are on the right. A visualization is on the left with alpha the arrival curve and beta the service curve. And that simplifies the model to the one shown on the lower right. Alpha bound entering a beta bounded server, creating an output departures that are bounded by alpha prime. Network calculus has some operations that help you to compute alpha prime from alpha and beta, even in the presence of cross traffic. We will come to them as we go through the slides of this presentation. We will need these operations to answer the question how to derive an end-to-end delay bound for some flow of interest, here denoted FOI, that is bounded by an arrival curve alpha as well, and on its sequence of servers that it crosses see some cross flows, here denoted F1 and F2, both bounded by a known arrival curve. And in the FIFO analysis there is an established method that is called least upper delay bound. It operates basically in 3 steps. Step 1 being computing the nesting tree of the given scenario, the network. The second step is to compute an end-to-end service curve by removing the crossflow step by step. So we have a minimal service curve that bounds the service offered to just this analyzed flow of interest. And last, we use that again with horizontal deviation to compute the end-to-end delay bound for the flow of interest. In order to start the LDB analysis, we need to know what nesting is. It's a property of sequences of servers, and it is regarding the flows that cross these sequences, also called tandems of servers. There are 2 properties. The one is if paths of flows are totally disjunct, then the tandem is nested, or if one path is entirely included in a different flow, then we also have a nested pattern. Any combination builds then also a nested pattern, and we call the tandem nested. Looking at the example to the left, we immediately see that we cannot execute this first step because at server 2 we have neither of the 2 properties. For this very reason, the least upper delay bound method actually has a preceding step, and that step is to cut such non-nested tandems, as in our example, into sequences of nested subtandems. In our example, there are 2 alternatives. As we saw at server S2, there is this non-nested pattern, and if we cut the crossflow F1 before or crossflow F2 after S2, the 2 subtandems will be entirely nested. We have a cut either here or here, and note that we do not cut the analyzed flow of interest to preserve the end-to-end view on it and to derive an end-to-end delay bound for it. The big problem of this approach is that neither of the 2 alternatives is strictly better than the other. We need to execute both analyses, and we need to compare the resulting delay bounds, and we need to take the least of these 2 bounds as the final result, hence the name least upper delay bound method. Now that we have a sequence of nested tandems, let me show you how the LDB analysis proceeds. The nesting tree is as follows. On the uppermost level we have the flow of interest as it crosses all the servers in the sequence. Then this F2, let's call it prime, to the right at server S3 is only nested into the flow of interest. On the left side, the 2 servers S1 and S2, we have flow F1 being nested in the flow of interest and flow F2 being nested into flow F1. That is the nesting tree, and from the nesting tree we can derive a network calculus term to compute the flow of interest end-to-end delay bound. It is quite straightforward. As said, we have at server 3, whose service curve is beta 3, we have the flow F2 prime, and in order to remove its impact to derive a leftover service for the analyzed flow of interest, we just use this binary O- operation. The same we do on the left side. We have at server S2 the impact of crossflow F2, and at server S1 additionally this O times is convolution that concatenates the service of 2 servers. We have there the impact of F1. Now we have 2 leftover service curves for these 2 subtandems. We concatenate them as well with this O times operation, and that is basically the first couple steps of the LDB analysis. Computing the alpha prime F2 is achieved with this part of the term then, and it includes a new operation, the deconvolution, that unfortunately adds the original arrival curve's burstiness again to the network, meaning we cannot assume it to have been leveled off by traversing the tandems in sequence. That would be known as the pay multiplexing only once property, because we pay for multiplexing with a cross flows burst only once, and the LUDB cannot achieve this property when it is faced with non-nesting interference patterns. We have been motivated by the question, what can we do about it? And already in this basic 3-server tandem example, we found out that the so-called flow prolongation feature, if added to the LDB method, can help compute better bounds. How does it work? That is quite simple. We see that if we prolong this flow F1 over the last server F3, we create a nested tandem. This creates a tandem that is more pessimistic as there is added interference at the last server, so results derived on this tandem will be valid for the original tandem as has been shown in the literature. Regarding the LUDB analysis and the network calculus term that is derived during the analysis, what we see is that in this term below there is no deconvolution anymore. Therefore, we do not face the problem of not having the PMOO property in the analysis, again, traded off against this additional interference at this last server. We are not only interested in a method that derives tighter delay bounds, but we are also interested in one that scales well with network size. And the flow prolongation feature, unfortunately, has been shown to not help in that regard, quite contrary. If we look at the small example on this slide, we see that the two crossflows F1 and F2 each have prolongation alternatives, and if we search through the entire space of prolongation alternatives, we end up in a combinatorial explosion. It cannot be done exhaustively. For the paper at hand, it turned out, even if we consider this extra condition that we want to convert non-nested tandems into nested ones, it does not scale either. Thus, we decided to employ machine learning to predict the probably tightest alternative of prolongations of different flows. To be precise, we employed a graph neural network where network calculus networks like shown on the left are converted into a graph neural network representation where we have these additional nodes shown in gray here that are associated with weights to be predicted and to give us then a ranking between combinations of individual flow prolongations. Our method is called DeepFP. To give you a high-level overview and intuition on our contribution, I brought this summarizing figure. On the left-hand side, there is the original workflow presented in the 2017 paper, where there still was the proposal of an exhaustive search, meaning we create all flow prolongation alternatives for a sequence of servers. Each alternative needs to be analyzed with network calculus, giving a delay bound, and the final bound is then, of course, the minimum amongst these intermediate results. With this paper's contribution, we just replaced the exhaustive search with a transformation of the network into a graph neural network. We get a prediction out of this graph neural network, or if we wish, we can get multiple predictions even. Then we analyze with network calculus again and get a delay bound. In the very fastest case, we only take one prediction and derive one bound. There is related work on network calculus and graph neural networks. This representative succession of 3 papers gives background especially on the transformation of the network calculus network to graph neural networks. But based on this, none of these papers is concerned with the analysis of FIFO systems that is usually the most complex in network calculus and thus needing the most efficiency improvements. Let me finish my presentation with some evaluation results. This is an excerpt from the paper where there are many more aspects that have been evaluated. On the left side, there is an evaluation regarding the delay gap to the least upper delay bound method, which is giving the improvement that we can achieve if we add flow prolongation to the LDB method. We have deep FP in 3 versions. The one without an index means we only took one prediction from the graph neural network. The others took more. And what we see is that the amount of predictions did not really change the result much, which in turn means that the graph neural network works quite well. It can really predict the best alternative in one attempt. And compared to a random heuristic with up to 32 randomly chosen flow prolongations, we achieve a quite larger improvement of the delay. We pay for this improvement with additional computational effort, which is shown on the right. The exhaustive flow prolongation search on the very bottom is very expensive, as already mentioned in this presentation before. And with increasing number of predictions or random choices, we also increase the runtime of the analysis. Compared to the original LUDB without prolongation, we see that the best performing one is deep FP on the GPU, which also gives a very good delay gap. So this is our new analysis of choice. This is all I wanted to present today. Thank you for your attention, and at the conference I'm now open to questions.